Imagine a wire, not as a solid, unyielding thing, but as a crowded highway for tiny particles called electrons. These electrons aren't just sitting still, they're constantly jiggling and bumping into each other. It's a chaotic dance of countless particles. Now, introduce an electrical source, like a battery. This acts as a pump, creating an electrical pressure that urges the electrons to move in a specific direction. Think of it like a water pump pushing water through a pipe. This pressure is what we call voltage. It's the force that motivates the electrons to get moving. The electrons, already in motion, begin to drift collectively towards the positive end of the battery, like a slow-moving current in a river. It's not a fast rush, but a gradual shift. This drift, though slow for individual electrons, creates a rapid chain reaction, passing energy along the wire almost instantaneously. Imagine a line of dominoes. The first one falls slowly, but the effect travels quickly down the line. But what happens to the electrons after they deliver their energy? They don't just disappear. The wire is a closed loop, a circuit. The electrons continue their journey, returning to the negative end of the battery, ready to be pumped again. It's a continuous cycle, a never-ending flow. Think of it like a train on a circular track. The battery provides the energy to keep the train moving, and the electrons are the train cars, carrying the energy around the circuit. Now, what if the wire is too thin? Or what if there are too many electrons trying to squeeze through at once? This creates resistance, like a narrow pipe restricting the flow of water. Resistance converts some of the electrical energy into heat, which is why wires can get warm when electricity flows through them. The higher the resistance, the more heat is generated. This is also how a light bulb works. The filament inside the bulb has a very high resistance, causing it to get so hot that it glows. So, next time you flip a light switch, remember the tiny electrons, constantly jiggling and bumping, being pushed along by the voltage, delivering energy and then returning for another round. It's a microscopic dance of energy that powers our world. The flow of electrons isn't perfectly smooth. There are always some obstacles and imperfections in the wire. These imperfections cause the electrons to collide more frequently, further increasing resistance and heat. It's like driving on a bumpy road. You'll experience more friction, and your car will use more energy. The type of material the wire is made of also affects the flow of electricity. Copper, for example, is a good conductor because it has many free electrons. They can easily move and carry charge. Rubber, on the other hand, is an insulator because its electrons are tightly bound and cannot move freely. That's why electrical wires are typically made of copper and covered with a rubber coating. The copper carries the electricity, and the rubber prevents it from escaping. Understanding how electricity flows in a wire is fundamental to understanding how all electrical devices work. From the simplest light bulb to the most complex computer, they all rely on the movement of electrons through circuits. So, the next time you use electricity, take a moment to appreciate the amazing microscopic world that makes it all possible. It's a world of constant motion, energy transfer, and fundamental physics. That rapid chain reaction is how energy passes along the wire. Now, as the electrons flow, they encounter resistance from the atoms within the wire. These collisions impede their progress, converting some of the electrical energy into heat. This is why wires can get warm when electricity flows through them. Think of it like trying to run through a crowded room. You'll bump into people, slowing you down and generating heat from the effort. The amount of current, the rate at which electrons are flowing, depends on both the voltage pushing them and the resistance opposing them. It's a delicate balance. A higher voltage means a stronger push, leading to a greater current. Imagine a powerful waterfall pushing more water through a narrow channel. Lower resistance allows electrons to flow more freely, also increasing the current. Think of widening that channel. More water can rush through with ease. To understand this better, let's consider a simple analogy. Picture a garden hose connected to a water faucet. The water pressure from the faucet represents voltage. The width of the hose represents resistance. If you increase the water pressure, voltage, more water flows through the hose, current. Similarly, if you use a wider hose, lower resistance, more water flows through, even with the same water pressure. Now, let's apply this to our wire. The voltage from the battery is like the water pressure, and the resistance of the wire is like the width of the hose. A higher voltage pushes more electrons through the wire, and a lower resistance allows them to flow more easily. This continuous flow of electrons, driven by voltage and influenced by resistance, is how electricity travels inside a wire, powering our lights, devices, and the modern world. It's a fundamental principle that underpins much of the technology we rely on every day. Without this flow, our world would be a very different place. Consider a light bulb. The electricity flows through the thin filament inside the bulb. The filament has a high resistance, which causes it to heat up intensely. This heat generates light, illuminating our surroundings. Or think about your smartphone. The battery provides the voltage to drive the flow of electrons through the intricate circuits. These circuits control the various functions of the phone, from making calls to displaying images on the screen. Even something as simple as a switch relies on this principle. When you flip a switch, you're either completing or breaking the circuit, allowing or stopping the flow of electrons. This control enables us to turn devices on and off at will. So, the next time you use electricity, remember the tiny electrons, constantly flowing and bumping, driven by voltage and influenced by resistance. They are the unsung heroes powering our modern world. Let's delve a little deeper into how these principles manifest in everyday devices. Think about a toaster. When you press the lever, you complete a circuit that allows electricity to flow. The heating elements inside the toaster have a specific resistance, causing them to heat up and toast your bread. The darkness setting on the toaster adjusts the amount of time the electricity flows, controlling how much the bread is toasted. Or consider an electric kettle. When you switch it on, electricity flows through a heating element at the bottom. This element's resistance causes it to heat up rapidly, boiling the water inside. Once the water reaches boiling point, a thermostat breaks the circuit, stopping the flow of electricity and preventing the kettle from overheating. These examples highlight how voltage, current, and resistance work together to power the devices we use daily, often without a second thought. It's a testament to the ingenuity of electrical engineering.